Potential energy, I remind you, potential energy pertains only to conservative forces. That is to say, a force such that the work it does is independent of the path taken from the beginning to point at the end point. For a conservative force F, the potential energy at point P is minus the integral of F dr from some standard reference point up to the point P. It physically is the amount of work you had to do fighting against the force F, the minus sign, the work you had to do to move an object from this universal reference point up to the point P. Now I ask the following question. How much work must you do if you don't move it from some standard reference point, but you move it from one point A to some other point B? Again, fighting against this force F, so the amount of work you would have to do is the integral of force times distance, but minus F because it's the force you exert, the force that it exerts, and this time going from point A to point B. So here's the situation. Here's the point B, here's the point A, and let's say here's our reference point back down here. One way that I could calculate that integral would be, first of all, to integrate all the way from the reference point up to B, and then subtract off the integral up to A. And the difference would be the integral from A to B. So I could write this, if I like. It seems cumbersome, but minus the integral from 0, the reference point, all the way up to point B of F dot dr, minus the integral from the reference point up to A of F dot dr. Make sense? In other words, instead of just going along this path here, I'm going to go along this entire path and then subtract off what I got for the first piece of it. What's the point of doing this? Well, you recognize here is the potential energy at point B, and here is the potential energy at point A. So this is nothing but U of B minus U of A. So there's a handy expression that the work you must do to move an object from point A to point B is the potential energy at the end minus the potential energy at the beginning. Make sense? By the way, this difference here, which is given by that integral there, makes no further reference to the reference point, which is why I've said several times that when in the physical context, there's always differences of potential energy that matter, and for them, the reference point disappears from the problem. Okay, so I just wanted to show you that the work done in moving an object from point A to point B can be written as the difference in the potential energy at the end point minus at the beginning point. Now, what is all this structure for? I come finally to the proof. I'll put that in quotation marks for reasons you'll see in a moment, of the law of conservation of energy. We've used the law of conservation of energy in a bunch of problems, but if you look back logically, I never did prove it. I simply said it at one point, and we started using it. Now I'm going to prove it. It's just logically backwards, but maybe pedagogically okay. I think sometimes it's better to save the proof until you really understand concretely what the theorem is saying. Mathematicians, of course, love to do it in the other order, to give you the details of the proof before you really understand what the theorem is. Anyhow, okay, proof of the law of conservation of energy. Must be humid today. It goes actually pretty simple. when you come down to it. Suppose that I have now the general case where there are both conservative and non-conservative forces acting. So there's gravity and there's friction or something like that. I ask you the question, what's the total work done by all the forces acting as you move an object from point A to point B? Watching very closely, you'll notice that I have switched the actor in this game. Now, I'm asking the work done by the forces. I'm not talking this time about the work that you did fighting against the forces. I'm talking about the work done by those forces themselves, which is going to be the same but with the opposite sign. So, W total is going to be the work done by the conservative forces, let's call it W sub C, plus the work done by the non-conservative forces, let's call it W sub NC. Is that notation perfectly clear? Put a footnote there. The total work done is the work done by the conservative forces, plus the work that's done by the non-conservative forces. But I happen to know what work is done by the conservative forces. Those can be represented by a potential energy function, and the work done in moving from A to B is minus U at B minus U at A. Damn, why minus? I thought the guy just proved that it was plus UB minus U. No, that was the work you have to do. And now asking a different question, how much work did the forces themselves do? That's opposite. So, minus this. The work done by F, not the work done by me. So that's the work done by the non-conservative, by the conservative forces. It's just given by this formula here, only with a minus sign because I switched the perspective, plus W and C, the work done by the non-conservative forces, and not much I can say about that. However, we happen to know what the total work done by all the forces acting is. That's equal to the change in kinetic energy. Why? Work energy theorem. Remember that right back from the beginning. Work energy theorem, which actually follows straight from Newton's second law of motion. Not straight. It's a convoluted argument, but it followed from Newton's second law of motion that the total work done by all the forces acting on an object is equal to the change in kinetic energy. So what does this say? The change in kinetic energy, that is to say, the kinetic energy at B minus the kinetic energy at A, is equal to, on the right-hand side, U minus U of B, minus a minus is plus a U of A at A, plus the work done by the non-conservative forces. I plan to pull this U of B over to the other side where it will pick up a plus sign, and likewise the U of A over to the other side where it will pick up a minus sign. And what's the conclusion? K at B plus U at B minus K at A plus U at A is equal to the work done by the non-conservative non-conservative forces. What does that tell me? On the left, in those two square brackets, I have kinetic energy plus potential energy, what you might call the total mechanical energy. In fact, let's do that. E sub m equal k plus u, potential energy plus kinetic. And the m is for total mechanical energy. Then what's my theorem here say? It says that the total energy at the end of the process minus the total energy at the beginning of the process is equal to the work done by the non-conservative forces. It says delta E sub m, if you like, the change in the mechanical energy of the system is equal to the work done by the non-conservative forces. What can I conclude from that? You actually saw a beautiful example of this on the OWL, I think for Monday, I think it was. Remember the problem where a cart is going along on a track that goes down a dip and then rises up some, and then it hits some gravel and it comes to rest here. In that case, you had some kinetic energy at the beginning, some kinetic and potential energy up here. It was eventually delivered all into the form of heat by the non-conservative frictional force. That was an example where the change in mechanical energy, kinetic here, potential mgh here by the end after it had come to rest, was equal to the work done by the non-conservative force. That was the work done by friction during this little piece here. I wish I had saved that and had it on today's OWL instead of before. I was using it as an example of something a little bit different back then, but a perfect example for now. Well, what do I make of this? Suppose no non-conservative forces act. If there are no non-conservative forces present, no friction or anything like that, then the change in mechanical energy is zero. Which is to say that the mechanical energy is conserved. That, folks, is the best I could do in classical mechanics to prove the law of conservation of energy. What it says is, if there are no non-conservative forces acting, then the mechanical energy is conserved. Well, it sounds almost like a tautology, but I now know what a non-conservative force is. A non-conservative, if I said a non-conservative force is a force that doesn't obey conservation of energy, then of course there would be a tautology. But if I say a non-conservative force is a force that has the special property that the work it does in going from point A to point B depends on the path, then I have characterized what a non-conservative force is, which you use a different word for really. But as long as no forces of that type are acting, then the total mechanical energy, kinetic energy plus potential energy, is always going to be conserved. That's the law of conservation of energy. But if non-conservative forces do act, then all bets are off. That's weird. I thought the law of conservation of energy was universal. Yes, it is. We believe the law of conservation of energy, absolutely, even when non-conservative forces do act. But you know what? You can't prove that from classical mechanics alone. You have to go to the theories that describe other forms of energy, like thermodynamics, describing heat energy. If you throw thermodynamics into the pot, then you can cover non-conservative forces like friction that deliver heat, deliver mechanical energy into the form of heat. But until you've got a theory of heat, you can't possibly prove the law of conservation of energy just from the mechanical part alone. Then if you want to talk about light and electromagnetic energy, you better go to a theory on electrodynamics that will have built into it some kind of an accounting for energy that's delivered into the form of light or something like that. It's only when you've assembled all of the different theories that you would be able to prove the law of conservation of energy in general. In the context of classical mechanics, I'm sorry, you can't do it. All you can do is prove that if there are no conservative forces acting, then energy is conserved. That's fine as far as you're dealing with gravitational systems or something like that don't have any friction in them. But once friction is in the story, all I can do is tell you, well, friction takes some of that energy and dumps it into the form of heat. But as far as mechanics is concerned, we can't get our hooks into that because it's not in the theory. I didn't know. That's why I put the proof in parentheses, in quotation marks there, because it is not really the grand proof of conservation of energy. Obviously, conservation of energy in the grand sense is something much deeper that overlies all of the theories of physics. And it would be nice to go at it from that perspective, but not at this level. And now for something completely different. Well, not completely different. We are still assembling. Remember, a while ago I said that Newton's laws, F equals ma in particular, form kind of like the ground floor of mechanics. And then the first story, a more abstracted level of the subject, involves concepts like work, power, and energy. We're now going, if you like, to the third floor, yet another layer of abstraction, where the critical quantities are momentum and impulse, but particularly momentum. Momentum is a word that we use in the everyday language, and what does it say then? If I say something's got a lot of momentum, think about it. It's got a lot of momentum. I don't know quite how to define that, but somehow or other it's telling you that this thing is going to plow through anything. Isn't that right? It's got, you know, it's not going to stop. Momentum, in a way, is a measure of how hard it would be to stop the thing. If something's got a lot of momentum, it's just going to barrel on through no matter what. So what is that? It's kind of a concept like inertia. Inertia or mass is the opposition to motion, opposition to acceleration, actually. The bigger the mass, the harder it is to accelerate the thing. But momentum also has velocity in there because it's how hard it is to stop the thing. So, what I'm trying to do is chatter about the notion of momentum to kind of motivate now the technical definition. Momentum is going to depend on the mass of the object and also on its velocity. Well, you say kinetic energy. Yes, that's right. There's another quantity that depends on mass and velocity. But momentum is defined as the mass times the velocity. Again, you can't quarrel with that as a definition. The question is whether it's going to be useful to us. Yes, it's going to be useful to us. Notice that it's a vector. It inherits the vector quality of v, mass times velocity, so it points in the direction of motion, just as velocity does. The units, well, the units of momentum would be units of mass times velocity, so kilogram meters per second. For some reason, no enterprising person has ever attached his name to that combination of units. I don't know why. It's almost unique in classical physics that nobody has thought to attach their name to it. So I have a proposal. I propose to call this unit the Griffiths. A Griffiths is 1 kilogram meter per second. I've suggested this in the past, and somehow or other it has not caught on. I don't understand why. I think the point is that the word Griffiths is almost as hard to say as kilogram meter per second. It's not my fault, by the way. I never learned how to pronounce that name. But actually, it's an unpronounceable name. The word is Griffith, but in Welsh, that's a first name, not a second name. When the English invaded Wales, over 1,000 years ago, one of the many atrocities that they committed was to insist that all Welsh people have intelligible names from the English point of view. So they would say, son of Griffith, and that became Griffith's son, but that was too complicated, so they just dropped off the O-N and it became Griffiths. The reason it's unpronounceable, in case you're interested, as I know you are, is it's a product of English imperialism. The proper name is Griffith. The English stuck that S on there, and that's why it's unpronounceable. And that, I suppose, is why the Griffith was never caught on as a unit per kilogram. Where? So, Newton's second law of motion can be written very nicely in terms of momentum. As follows. Suppose that I calculated the derivative of p. I'm talking about some object is moving around and forces are acting on it, or something is speeding up and slowing down and whatnot, and I'm interested in what is the rate of change of that momentum. Well, that would be d by dt, the rate of change of m times v. The mass is not changing typically. Actually, you can encounter, and we shall, when we study rocket motion, contexts in which the mass of the object itself is changing because you know it's spewing fuel out the back end or something like that. But the typical situation, mass is just a constant in here. It comes out in front, and I've got m times v dv by dt. But dv by dt, the rate of change of velocity, is acceleration. This is m mass times acceleration. But mass times acceleration, according to Newton's second law, is F. So what's the conclusion? F, which we've always written as ma, could also be written as dp by dt. In some respects, that's a nicer way to write it. It's the way that Newton himself always favored. Newton tended to write the second law. In fact, I'm not sure you will ever see in Newton's own work the second law written as F equals ma. It's always written as force equals rate of change of momentum. It's a cute way to write the second law. And I'll show you one of the reasons why it's such a cute way to write the second law. It affords a very quick derivation, or way of thinking about a new law, the law of conservation of momentum. Not a new law, it follows from Newton's laws. Conservation of momentum. Imagine the following situation. In due course, we'll come up with more complicated context for the conservation of momentum, but I want to illustrate the sort of guts of the theory, the essential point in the law of conservation of momentum. Suppose that I have two objects here. I'll call them A and B, and they're interacting with one another. But they're the only two objects in the universe, if you want to be clean about it, so they're only interacting with each other. I don't need to worry about somebody else's influencing the situation. One way to set this up would be to have an air cart here and two carts on the air track, and they're bouncing off each other. So when they collide with one another, you say, oh, wait a minute, there's gravity acting down, yeah, there's a normal force acting up, there's a tiny little bit of friction. But the force in the vertical direction are actually irrelevant as far as the motion in the horizontal direction is concerned. If that's too complicated a situation for you, the billiard balls on a billiard table, there's another example, two billiard balls, they smash into each other or something. Again, there's gravity and normal forces acting, but they're perpendicular to where the action is, so they don't matter. If you want the cleanest example, take two asteroids out in empty space, and they're gravitationally attracting each other and maybe whirling around. I don't know what's going on, but the point is, I want two objects that interact with one another, but nobody else is touching them. no other relevant influences, no other forces that are relevant to the problem. I don't know what the forces of interaction between those two are. If you were talking about colliding billiard balls, actually, if you stop to think about it, the force involved in the collision would be monstrously complicated. We don't have the foggiest idea what that is. It would be huge for a brief split second while those two things are in contact, and then it's zero when they pull apart. So that would be a god awful problem to figure out what the actual force is when two billiard balls collide. But I'm never going to need that. One thing I do know about those forces is whatever they are, they obey Newton's third law. Newton's third law, which says that the force on A, due to B, of course, that's the only thing in the problem, is equal and opposite to the force on B due to A. That's the only other thing in the problem. So it's minus F on B. Is that an okay way to write it? The force on A due to B is equal and opposite to the force on B due to A. Let me rewrite that in terms of this version of Newton's second law. This says dP, the rate of change of momentum of object A by dt, is equal to minus dP B by dt. The rate of change of the momentum of A is equal and opposite to the rate of change of the momentum of B. What does that tell us? That says that if A is increasing its momentum, then B must be decreasing its momentum, and in exactly the same amount, at exactly the same rate. Actually, let me pull a dP by dt over to the other side and write this instead as d by dt of the sum PA plus PB. That's got to be equal to 0. You see how I did that? Pull this over to the other side. Now I've got the derivative of PA plus PB. The derivative of the total momentum, if you will, the sum of the two, is equal to 0. What does it tell you if I say that the derivative with respect to time of something, some quantity, is equal to 0? It's constant. It's constant, right? It's not changing at all, because this is the rate of change of the sum PA plus BP, and it says that the rate of change of that sum is equal to 0. So the sum of those two is constant, it's not changing. PA plus PB is constant. Or, as we would say in a little bit fancier language, the total momentum is conserved. The total momentum, A and B together, is conserved. It's the same after any process, such as a collision of those billiard balls, as it was before. And for that matter, it's the same all during the collision, too. Although I probably wouldn't care to analyze the details during the collision, but the important point is it's the same afterwards as it was before. That's the law of conservation of momentum. And it follows just from Newton's third law of motion. Well, and Newton's second law of motion in this form. But it does not depend on me knowing anything whatsoever about the actual forces that act between those two. It's astonishing. All I've got to know is that A and B are talking to each other, and there are no other relevant forces acting on the system. Then the total momentum, A plus B, has got to be a constant, regardless of what the forces that are acting are. A very, very powerful law, because it enables you to get your hooks into a lot of problems where you don't know what the actual force acting is. Conservation of energy is all well and good, but at least in the mechanical context, you've got to know, was this a conservative force or not? At least you have to know that much about it. Conservation of momentum, I don't care. If A is interacting with B, then the total momentum is conserved. Let me run a bunch of examples here, starting with a very trivial one and building up to fancier and fancier ones. suppose that I've got two carts on the air track, and here they are, and I'm going to stick in some sensible numbers so I don't get bogged down in arithmetic. This is 10 kilogram cart. That's one hell of a heavy cart, but forget about it, it's a nice number. 10 kilogram cart is going along at 5 meters per second. When it encounters another cart, which is 6 kilograms, and it's going the other direction at 3 meters per second. So can you picture that? A 10 kilogram cart, fairly heavy one, coming along at 5 meters per second. A somewhat smaller cart going the other direction at 3 meters per second. They smash into each other. Why am I putting it on an air track, by the way? Why don't I do this on the ground? Well, I want to get all the external influences out of the problem, so it really is something close to just two things interacting with one another. Collision of two carts on the air track. This is the scene before the collision, and now I suppose that those two carts stick together. I don't know if you fiddle with those things, but maybe they got a Velcro coupler on there or something like that, so that afterwards I've got a combination of the two of them stuck together, a total mass of 10 plus 6, I guess 16 kilograms, and that's moving along at some velocity v, which I want to find out. So there's a classic conservation of momentum problem. I figure out what the momentum is before. I figure out what the momentum is afterwards in terms of that unknown v. I set the two equal, and I'll solve for v. So what's the momentum before? Let's call it P initial. By the way, this is all in one dimension, so I don't need to worry about the vector signs. But I do need to be very careful about the signs, because this one is going in the backward direction, this one's going in the forward direction. So this is a positive v, and this is a negative v. So what's the initial momentum? Mass times velocity. I've erased my definition of momentum, but P is equal to mass times velocity. So the momentum of this cart, 10 times 5. The momentum of the other cart, 6 times minus 3. Easiest way to screw up in this business is to be careless about the directions. This is going in the backward direction. If it were going in the other direction, to the right, there's a different problem. Okay, 5 times 10 plus 16 times 3, this is 50 minus 18 is equal to 32 Griffiths. That's the momentum before the collision. The final momentum after the collision, well, the mass is now 16, and the velocity is, I don't know, that's what I'm trying to find. Conservation of momentum says that the initial momentum, 32, must be equal to the final momentum, 16 times v. You can tell I made up these numbers, not the book or Al or something. 16 goes into 32. 2, v is equal to 2 meters per second. There's the answer. Do I know what the force of interaction was while those two things were bouncing off each other? No, I do not, but I don't care. It doesn't matter. As long as I don't ask about the details of the collision, but just how fast the thing is going afterwards. Very easy. Okay, second example. Suppose that we've got an ice skater here. Ice skater friction. That wasn't the ice skater. Here's the ice skater. There, the ice skate. And this ice skater is holding a snowball. There it is. By the way, I didn't tell you how much this ice skater weighs. 50 kilograms. And the snowball, let's see, this snowball, it happens, is 5 kilograms. And she's at rest. That's the scene beforehand. Just sitting there holding the snowball. Now she throws the snowball. So there goes snowball. And snowball is going at 20 meters per second.
Wow.
Ice skater, meanwhile, recoils in the backward direction. Question, what is her speed? Can you picture that? So throw the snowball, you recoil backward. What's the final velocity of the skater? So this is the scene after. By the way, not everybody likes to draw these little pictures, but they help me to think about conservation momentum problems. I always do this. What's the scene beforehand? What's the scene afterwards? And I know what I'm focusing on. So, beforehand, P initial, you tell me. She's standing there holding this snowball. Nothing's moving. Momentum is 0. P afterward. Afterwards. Well, I got a snowball here, and its mass was 5 kilograms, and it's going at 20 meters per second, so it's 5 times 20. Plus her, 50 times, well, I've drawn the picture here with V going in the backward direction, which is in fact the way it's going to be going. So let's put in V like that, with a minus sign. If you had a more complicated problem and you weren't dead sure which way she was going to be going, you could say, well, I'll keep all the velocities positive, put that in the positive direction with a plus sign here, solve the problem, and you would come out with a negative V. Then you would say, I must have guessed wrong. Actually, she's going in the backward direction. So it doesn't matter as long as you're consistent. But having drawn the picture with the velocity pointing to the left, I've got to put this in as a minus sign because that's a negative velocity. So what do I get? 5 times 20 is 100, minus 50 times V. Conservation of momentum says that the momentum before has got to be equal to the momentum afterwards. So 100 minus 50V is equal to 2. She recoils at 2 meters per second. Same as the velocity of this car over here. How about that? I should have made up different numbers. But conservation of momentum. In this instance, the initial momentum was 0, final momentum something or other. Do I need to know any details about how she threw that snowball? What the force was that she exerted on the snowball? Nope, that's the beauty of conservation of momentum. I don't need to ask about that. Okay, let's do something a little bit neater. I wanted to do 2 really trivial examples at the beginning to show you what the essential point of conservation of momentum is. One can make conservation of momentum problems, of course, as complicated as you like. So here's a little bit more complicated situation. I imagine that we've got a block of wood here, and somebody fires a bullet into it. So this is a 0.01 kilogram bullet, 10 grams for the bullet, and it's going at 500 meters per second. I don't know if that's a reasonable speed or not. It encounters a block of wood at 4 kilograms. And here is a bullet coming along. And I imagine that this bullet plows right through and comes out the far side. So here's the block of wood with now a little tunnel through the center of it. And the bullet comes out the far side, and it's going at 100 meters per second. Not as fast. How come? Because it lost some oomph going through this, going through the block. The block slowed it down, but not enough to stop it completely. The block, meanwhile, had better be going in the forward direction. In fact, the block will have picked up whatever is gone of the bullet momentum here. So this block is now going to be going to the right at speed v, and I want to know what that speed is. So here's the speed before, and here's the speed after. Conservation of momentum. The initial momentum is, well, the block isn't moving, so it's just the bullet here. The mass is 0.01 kilograms, and the speed is 500 meters per second. So that's 5 kilogram meters per second. P afterwards, what is that? Well, I've got the bullet, 0.01, and it's now going at 100 meters per second. But I've also got the block, 4 kilograms. I'm not putting the units here, so 4, and it's going at a speed v that is my business to find. See how it goes? Conservation of momentum says that those two are equal, so 5 is equal to, let's see, 0.01 times 100 is just 1, plus 4v. Pull the 1 over there, got 4 is equal to 4v, means that v is equal to 1 meter per second. I'm going to stop there. Next time we'll do some fancier examples of conservation momentum in 2 and 3 dimensions. By the way, I wanted to say one thing about the exam because several people have asked me afterwards, does this particular number mean some particular grade, or what fraction of the students in the class are going to get each grade? First of all, I wouldn't dream of grading a course like this on the basis of a single exam. But secondly, those rules don't mean anything to me. I don't have a preconceived notion of what number corresponds to what grade. I don't want to conceal anything from you, but if you're used to in high school that an 87 is a B plus or something, I don't know if an 87 is a B plus in here, and you're not really competing against other students, I would be delighted to give everybody in the class an A if everybody deserved it. So I don't grade on a curve in that sense of a certain, the top so-and-so percent is going to get touch. In fact, nor do I have a preconceived notion of what number deserves what kind of split. That was, I would say, a relatively straightforward, simple, and fairly short exam. And the scores were high, which delights me. I mean, I wasn't trying to throw any curveballs at you. I wanted to know if you basically learned the material, and my conclusion is yes. Almost all of you have mastered the material, and I'm delighted. So, but don't try to attach a particular number to a particular grade.